So we'll continue our foray into the chemistry of carbon. And one of the reasons why carbon is set apart from other elements and is used in the chemistry of life is because for three reasons. Carbon can form stable covalent bonds with other carbon atoms and other atoms such as nonmetals such as hydrogen, oxygen, nitrogen, and it also can form double and triple covalent bonds with itself and certain other elements. All this put together gives a great diversity to the element carbon, and that makes it perfect for the element of life, if you will. It's a specific subset of the chemistry of carbon were that of hydrocarbons, and we had looked at general ways that hydrocarbons can be put together. We saw that they could be put together in a linear form, which we see right here, where I've bolded out the carbons, and we see that the carbons themselves are in a linear form. Also in a cyclic form that we see here, as well as in a branched form that we see here. And lastly, specifically with respect to single bonded hydrocarbons, meaning the carbons, the carbon-carbon bonds were single bonded, we were able to classify each carbon of these hydrocarbons as primary, secondary, tertiary, or quaternary. So an interesting question when looking at some of these larger single-bonded hydrocarbons might be the difference in ease of counting the number of carbons with the number of hydrogens. It's much easier to count the number of carbons or approximate the number of carbons in a molecule than it is to count the number of hydrogens, because each carbon has 4 bonds emanating from it. It can accommodate a lot of hydrogens. There is a shortcut to this. Specifically, if we look at this over here on the upper left, we find an 11 carbon chain right here. And if we asked how many hydrogens are on it, we could draw in all of the bonds on each carbon to satisfy the rule of 4 and decorate them with hydrogens, or we could count the number of carbons and put them together in a very simple expression, 2n plus 2. That's the number of hydrogens per the number of carbons on a molecule. So if we had 11 carbons on the molecule, the number of hydrogens would be 2 times 11 plus 2, which is 24 hydrogens. Now, granted, we could very easily just draw all these hydrogens in and count them. This is a much easier way to do it. A constraint here is that the carbon-carbon single-bonded species must be non-cyclic. It can't have a cycle in it at all. It can be branched, however much density is needed. We'll look at that as well. But as long as it's not non-cyclic, or it is non-cyclic, we can get this 2n plus 2 expression very nicely. Now, if we do have a situation where we have a cyclic hydrocarbon, again, look at this as an example of a very large cycle right here of 22 carbons, we can easily count the number of hydrogens on it, or come to a number by, rather than 2n plus 2, using the 2n expression right here, with n being the number of carbons. So on this example here, if I had a cycle of 22 carbons, or any structure of 22 carbons with somewhere one cycle in it, I'm going to have 44 hydrogens, because that's 2 times 22 equals 44. So in both of these cases, as long as we recognize that we have either a non-cyclic or a cyclic system, the number of hydrogens on these carbons becomes elementary. So there are actually a number of different ways to draw these carbon compounds. One way that we've been drawing thus far is with the highest degree of complexity, the most information put forth, and that is known as the complete bonding structure. And here we have examples of a linear hydrocarbon, a representative branched hydrocarbon, a cyclic hydrocarbon, or a hydrocarbon containing oxygen or nitrogen, as long as it adheres to the standard bonding model. Here we have them written out here, examples of them And we can see that they have the highest degree of information with them, showing all of the carbon atoms, all of the hydrogen atoms, every carbon-carbon bond, every carbon-hydrogen bond, and so on. However, the Achilles heel, if you will, with this high degree of complexity and information and structure is a lot of effort to draw these. So we're going to introduce two ways in which we can abbreviate our efforts in expressing these or drawing these carbon compounds, while at the same time, as long as we keep to ourselves certain criteria and minds associated with each of these abbreviatory methods, we will have the same information associated with it. So the first abbreviated way of drawing carbon compounds is with respect to what is called the condensed structure. It is condensed. Now, the condensed structure essentially puts in or includes all the carbons and hydrogens as C's and H's, but takes away all of the bonds. The covalent bonds, those lines, we have to now infer that they're there. So let's look at the corresponding condensed structure compared with the complete bonding structure of our linear hydrocarbon. Notice this follows the parent chain, if you will, through this linear hydrocarbon, but it abbreviates or condenses the number of hydrogens connected to it. So notice this first carbon here on this complete bonding structure is connected initially to 3 hydrogen atoms. Well, that's given on the condensed structure as CH3. The next carbon on the complete bonding structure is connected to 2 other hydrogens given as CH2. And we go through this with 3 more, in this case CH2s, until we end with the terminal carbon here, which is connected to 3 other hydrogens, as given as CH3. Now we can use this condensed structure when describing branched hydrocarbon structures as well, as given in this next example. And the idea here is, how do we connect these two? How does this complete bonding structure equate with the condensed structure? And the way to do that is to follow what I would call a parent structure throughout that. Well, it is fairly obvious here that the parent structure, the parent carbon chain on this branched hydrocarbon would be this 4-carbon chain right here. And in so doing, now we can see, well, there's our carbon branching point. So we're going to follow through this condensed structure of this representative branched hydrocarbon as we move along, similar to how we did it last time. If we look up at the complete bonding structure, that first carbon, again, has 3 hydrogens attached to it, CH3. Moving to the next carbon, we have, that carbon has 1 hydrogen attached to it, CH, as well as this CH3 all by itself. And that's given parenthetically here, parentheses, CH3, closed parentheses. Then we move to the next carbon in the line. That is connected to 2 hydrogens, CH2, and finally the end one. Here we have that end one connected to 3 hydrogens, CH3. Now, condensed structure, for our purposes, we're only going to be using for linear hydrocarbons and branched hydrocarbons. Condensed structure with cyclic hydrocarbon or other element-containing molecules we won't consider here because, first of all, it can be confusing, and that there's a number of ways of doing this which are accepted in the general organic chemistry community, and to introduce all of them would similarly introduce too much confusion. So we will not be considering condensed structure with cyclic hydrocarbons or oxygen or nitrogen-containing molecules. By far the most common way of drawing carbon compounds is with respect to line structure. Line structure is the most abbreviated, so we have to keep in mind a number of conventions and assumptions as we move forward. So the first thing that we're going to consider, in line structure, there are always carbons implied at the ends and the bends. And what does that mean? Well, let's look at the line structure of this linear hydrocarbon here. it just sort of looks like a squiggle, doesn't it? Like a zigzag. However, if you'll notice, we have two ends here. Those are implied that there are carbon atoms there. And we have a number of internal bends in there. Those are also implied as carbon atoms. So that is the assumption. The other assumption is that at each of these ends and bends, or these carbons on these ends and bends, are sufficient hydrogens and their covalent bonds to satisfy the rule of 4. So let's look at this now, if you're over on the end here. So if this very end, this end right here, there's a carbon there, so that should be a carbon. We are assuming there is 1, 2, 3 hydrogens on there. So that's the assumption. They're not there, but we assume that they're there. So there's a carbon where that red dot is in the middle as well. That's a heck of an assumption, but it will get used to that, and thus it will make it much easier to draw these hydrocarbons if we can keep this in mind. Similarly, one of the inside bends, here's a bend right here. There is a carbon atom there. And the thing to ask yourself is, how many hydrogens are emanating from that carbon? And we have to think, well, there's the rule of 4. We have the rule of 4 around each carbon. So at this internal carbon, we have 1, 2 bonds already showing. So there needs to be 2 more. There must be 2 more. And those 2 more are implied hydrogens. So just like we did on the end, notice on the end one, we had to write 3 hydrogens. Why? Because we need a total of real and implied 4 covalent bonds emanating from each of from that carbon. So whether they're internal carbons or they're terminal carbons on this line structure, we imply that the carbon, each of the carbons has sufficient hydrogens to satisfy the rule of 4 for every carbon. And we can look up at the top in comparison and see that we indeed did this right. See, if we look up here, yes, there on that end carbon, there is 3 hydrogens. On the next one in, there are 2 hydrogens. We were able to figure that out. Why? Well, because we have to have sufficient hydrogens to satisfy that rule of 4. So in this case, we're able to do that. But look at this now. This again, the line structure is just a little squiggle as we see that here. Let's take a look at how our representative branched hydrocarbon now associates itself or gives itself over to line structure. Wow, that's much easier. Look at that. So that 4-carbon parent structure that we had touched on before, that's given right here, with carbons implied at the ends and the bends, and of course sufficient hydrogens on each carbon to satisfy the rule of 4. And look on the complete bonding structure now, that whole branch right there is given just as this one line coming off of it in the line structure. That's much easier. And as we practice these, we're going to hold that implication closer and closer so it becomes part of our lexicon so that we can understand the way that these are moving forward. I will say that moving forward, for the most part, as we go through the units in the organic chemistry, I will be moving to, as my default position, writing inline structure. So it will be important to be able to draw these and discern what exactly that they mean. So let's look at a cyclic hydrocarbon. Here's our representative cyclic hydrocarbon. What would this look like as a line structure? Well, when we start drawing cyclic hydrocarbons by line structure, it seems like we're back in geometry class. I mean, that looks like a pentagon or something like that. What we've done is we've we've just put in the carbon structure without putting any letter C's in there at all. There's 5 bends in there. Obviously, on a cyclic hydrocarbon, there are no ends because there's no beginning or end to a cycle. But there we go. If we see a pentagon or a triangle or a square, that would be representative of a cyclic hydrocarbon. We'll certainly be looking at that in the future. Now notice the assumption here is all of the C's and the H's are never shown in line structure, all of the carbons and hydrogens. However, if the molecule has other atoms in it, such as oxygen, nitrogen, sulfur, or chlorine, any other halogens, we do show those. So let's look now at our, in this case, this oxygen-containing molecule written here as its complete bonding structure, how this would be set up as a line structure. Now notice all of our carbons are now gone. We have our ends and the bends. So we have one carbon here and here on an end, and this is a bend right there. So we have 3 carbons. Yes, indeed we do. We can see that up top. But look at that double bond O. It is still a double bond, but that oxygen must be drawn. We have to draw this oxygen, nitrogen, sulfur, chlorine, anything but carbon and hydrogen. We do have to put those in, always. So let's look at some more complex examples, if you will. How about convert the following complete bonding structure into a condensed structure? So remember, we have 3 different ways of drawing these carbon compounds now, and the idea is, can we convert one into the other? Well, the idea, as before, is to follow, going from this complete bonding structure into a condensed structure, is to follow sort of a parent, underlying sort of parent carbon chain. And that would, the way this is written, it would be very helpful just to run it straight across like this. We'll look at each of these different carbons throughout. So this first one is a carbon connected to 3 hydrogens. So we'll write that as CH3. Next carbon directly connected to 2 hydrogens, CH2. The next carbon is directly connected to 1 hydrogen. We'll write that in as CH. And we have a branch point of a CH3 connected to it. So that's going to be putting that in parentheses as a CH3. Fair enough. We'll move along now. The next carbon is connected directly to 1 hydrogen, CH, and it has a CH3 branch on it as well. We'll put that in parentheses. The next carbon is directly connected to 1 hydrogen, CH, and now we have a branch of 2 carbons, CH2, CH3, in parentheses, the entire thing in parentheses. The next carbon is directly connected to 1 hydrogen, CH, and again we have a CH3 as a branch, CH3 in parentheses. Finishing this out, we have a carbon connected to 2 hydrogens, CH2, and lastly we have a carbon connected to 3 hydrogens, CH3. So here we were able to go through each of these carbon atoms in sequence, determining what is connected to them in both cases. So let's look next at the next exercise. Convert the following condensed structure into now a line structure. Well, we're going to do the same thing as we did before. We're going to look at this carbon by carbon. Remembering in a line structure, we imply carbons at the ends and the bends. So we have a CH3, that's 1 carbon, going to a CH2, 2 carbons together. I draw that here as here's that end carbon, and here is that internal branch carbon. Then we have a carbon which is connected to 2 CH3s. We have a double branch point off of that. So there's that internal carbon of the parent structure, and here are, on the end in red, the branch of 2 CH3s, 2 of them. So we've carried that out. So now we're going to go to our next carbon. That is a carbon, a CH, connected to a branch of CH2CH3. Again, that CH2CH3 I've put in red. Following that, we have a CH2, CH2, CH3, which is bend, bend, end, to finish out that structure. Now, of course, you can take some time to look at this and try to decide, okay, do I have this right number of carbons in the line? Is my branching okay? And so on. But it is going to be important to be able to move through these or to interconvert between the various ways of drawing carbon compounds. So with our four building blocks, carbon, hydrogen, oxygen, and nitrogen, we're able to put together pretty much an infinite number of possible molecules that can be put under the auspices of an organic structure. But we find that, indeed, these four building blocks, as they come together, while the number of molecules per se that we could make is in effect limitless, they do seem to come together, these four atoms, in certain repeating bonding patterns, which are predictable. We see them repeatedly and consistently in all of organic chemistry and in biochemistry. So really what I'm teeing up here is the entire remainder of the organic portion of this course is going to be based upon these things called organic functional groups. These functional groups are a repeating predictable bonding pattern of carbon, hydrogen, nitrogen, and or oxygen seen repeatedly and consistently in all organic and biochemical molecules. So we're going to be laying these out here, and at this point all we need to do is to be able to recognize what functional group we are looking at in each of these cases. So let's look at a number of functional groups that are only put together with carbon and hydrogen. Of those four elements, we'll only look at carbon and hydrogen. These are considered hydrocarbons. And let's take a look at the ways in which these can come, these predictable ways, recognizable ways that they can come together. So the first one is known in these hydrocarbon functional groups is known as the alkane. An alkane is typified by carbon-carbon single bonds. We find, really, that we've been drawing a lot of alkanes lately because we've been drawing almost exclusively molecules with carbon-carbon single bonds. So really, here is what we're looking at, this carbon-carbon single bond in this representative example. These R groups right here, they're not an element, they're not an atom or anything. They're a way of abbreviating a molecule. We'll talk about those on the next slide. But really what it's telling you is, like, this is the example I'm showing you right here, this carbon-carbon single bond. And we'll again look more at that abbreviatory nature of R on the next slide. If we should have a carbon-carbon double bond, that is known as an alkene. Alkenes are typified by carbon-carbon double covalent bonds. That's different than an alkane, which is a carbon-carbon single bond. Notice the difference, and also notice the very subtle shift between the names because they look the same. Alkane sort of looks like alkene. We've changed one vowel. That's going to be an important distinction, just changing one letter. If we have a carbon-carbon triple bond, that is known in functional group parlance as an alkyne. Alkane, alkene, alkyne. So again, we have these very similar names that we have to go with and be able to discern between. Alkane, alkene, alkyne. Carbon-carbon single bond, double bond, and triple bond. We'll be able to pick those out of molecules, and we'll talk about that as we move along. The last hydrocarbon functional group that we will be looking at is very different. And it's a very specific type of structure, but it is ubiquitous, meaning that we see it all the time or much of the time in organic molecules, and it's very recognizable. And this is known as a phenyl group. A phenyl group is a 6-carbon ring. Again, don't worry about that R right there. We'll talk about what that is presently. A 6-carbon ring with alternating double and single bonds. alternating double and single bonds. And you can see if we do set up that ring in that fashion, we have one more covalent bond allowable on each carbon, and that is capped with a hydrogen in each case. So the phenyl group itself, if I had to encircle this, would be this structure right here. Very recognizable. And we'll be seeing this. When we see this again, I'll remind you, hey, that's the phenyl group we've been looking at, and it'll get to the point where it is quite recognizable. So let's talk a little bit about what those red R's were on the previous slide. When we write R, R is an abbreviation in organic chemistry. It's an abbreviation for sort of the unimportant remainder of a molecule. So let's look at this molecule over here on the left. And I've already emphasized the alkene on it here. If I just wanted to have bring your attention to this alkene portion right here. And it said, look at this alkene, look at this carbon-carbon double bond. There's a lot of other shrubbery here, which I like to call it, just extra carbon structure, which isn't important to the argument or the attention I'm trying to have you draw to a particular portion of that molecule. What I can do is, since this architecture here and here is sort of meaningless, what I can do is just replace that with the letter R. It abbreviates the hydrocarbon type framework, which we don't care about, as this R group right here. So R, in this case, is this unimportant portion, at least unimportant with respect to the argument we're talking about in this molecule. And this R right here represents the rest of this portion right here. So it abbreviates the hydrocarbon framework so that the focus can be on that functional group, in this case itself, and we don't have to be confused or taken away by looking at this or looking at this, while our attention really should be on this. And as we can see, that abbreviation right here, it really distills it down, so we're really just looking at that alkene. So let's look at some other functional groups now. We've talked about 4 functional groups we just named that only consisted of carbon and hydrogen. Well, we have a couple others of these to recruit, and these are oxygen and nitrogen, these oxygen and nitrogen atoms. And when we bring these into the fold, the number of possible ways of putting them together into functional groups increases significantly. So let's look at these one by one. If we had, for instance, a hydrocarbon type carbon, notice that is a carbon with only other hydrogens and carbons attached to it. That's why I call it a hydrocarbon type carbon. That is connected directly, or rather covalently bonded to an oxygen, which is in itself connected to a hydrogen. What we have then is what is known as an alcohol functional group, an alcohol. So there is not 1 or 2 alcohols out there. As long as it has an OH attached to a hydrocarbon type carbon, it is known as an alcohol functional group. If we had an oxygen which was flanked on both sides, now remember, oxygen, it has 2 covalent bonds emanating from it. That's the standard bonding model. So if those 2 covalent bonds are attached to 2 hydrocarbon type carbons, then what we have is an ether. That's an ether functional group, when we have an oxygen atom flanked by 2 hydrocarbon atoms. Let's bring nitrogen into play. If we recruit a nitrogen and we have a nitrogen atom in any fashion flanked by at least 1 hydrocarbon type carbon, then we have the functional group amine. That is an amine functional group. So Now that we've recruited oxygen and nitrogen, there'll be plenty more of these as we move along to subsequent slides. We can already name 3 new functional groups to go with the 4 ones from the previous slide: an alcohol, an ether, and an amine. Now, I'm going to back up and just bring into play a couple other types of elements other than carbon, hydrogen, nitrogen, and oxygen that can decorate a carbon framework. And these would be known as the halide functional group. It is a halogen atom, single bonded to a hydrocarbon type carbon. Now, as we know, we have 4 halogens that we typically work with. 4 of them. That is fluorine is a halogen, chlorine, bromine, and iodine. Any of these is considered a halide functional group, that HAL for halogen. Any one of these 4 would be considered as a functional group a halide. So there are 5 remaining functional groups, all of which are related by the existence of what is known as a carbonyl group. A carbonyl, meaning all of them have a carbonyl. A carbonyl is a C double bond O. And if I have a C double bond O, you may notice that while the oxygen doesn't have any other bonds associated with it, because oxygen can only have 2 bonds emanating from it, the carbon of the carbonyl must have 2 other covalent bonds emanating from it to satisfy the rule of 4. How those covalent bonds attach on either side of the carbonyl gives us a diversity of functional groups. We can name 5 new functional groups related by the fact that they all have a carbonyl group within them. So let's look at these. First one, we'll talk about our carbonyl. So if I have our carbonyl here, there's a C double bond O. And those 2 additional bonds emanating from carbon determine the name of this functional group. So if we have our functional group, in this case, our carbonyl flanked on one side by a lowly hydrogen, and on the other side by a hydrocarbon type carbon, we have what is known as an aldehyde functional group, an aldehyde. The next one, if we have our carbonyl carbon, and it is flanked, and this is different than an aldehyde, flanked on both sides by 2 hydrocarbon type carbons, we have what is known as a ketone functional group. A ketone, notice, that is different than an aldehyde, even though both of them have a carbonyl type of structure in them. Next, here is our carbonyl, and let's see what 2 types of structures it is flanked by. A carbonyl flanked on one side by hydrocarbon carbon, and on the other side by a nitrogen in any form is known as an amide functional group. An amide functional group. Now, we've already seen a nitrogen-containing functional group. That was an amine. And that had a nitrogen directly covalently bonded to a carbon. So why is this one called an amide when the other one was called an amine? If you remember, and you may need to go back and look at this, the definition of an amine was a nitrogen covalently bonded to a hydrocarbon type carbon. In this case, with an amide, it is a nitrogen covalently bonded to a carbonyl carbon. It is a carbonyl carbon, not a hydrocarbon type carbon, which means that carbon is attached to hydrogens, other hydrogens and other carbons. This one, carbonyl carbon, is attached to an oxygen. That's different. Slightly different structure. If it's a slightly different structure, it must have a different designation. This takes practice. It's going to take practice to discern between them, and that is why I'm sort of dumping a whole lot of them on you right now, but we are going to have plenty of time to work through these. All right. The next one, we have a carbonyl. Here is our carbonyl group, and it is flanked on one side by a hydrocarbon type carbon, and on the other side by an oxygen, which is in itself covalently bounded to a lowly hydrogen. If we have all that put together, we have the functional group carboxylic acid. Carboxylic acid. And let's look at the last carbonyl containing functional group. It's similar to a carboxylic acid. If we have a carbonyl flanked on one side by hydrocarbon carbon and on the other side by an oxygen, which now in itself is covalently bonded to a hydrocarbon type carbon, I know this gets repetitive, then we have what is known as an ester functional group. An ester functional group. So if we look at these, we can pick out the slight structural differences which discern between them, which make them different than one another. So let's perhaps take a look at how we might be asked to pick these out of a lineup, so to speak. So here now we have a big scary molecule. Try to put aside these circles there, but if you can see what we have below it, we have a very large molecule drawn in line drawing. If all of these shapes put together, this is, if we look at every end and every bend, we have carbon atoms in there, if they don't have something in there already. Some of these carbon atoms are already enunciated because these are the functional groups I've just chosen to put them in. But this is how these molecules are going to be presented, as I said before, almost exclusively in the form of a line drawing. And essentially what we have is a bunch of functional groups perched upon a framework. Now this framework, the framework of these molecules is carbon-carbon single bonded. So we could really say that since alkanes are carbon-carbon single bonded, the vast majority of this molecule would be alkane structure, carbon-carbon single bond. And we'd be right. However, almost never would I ask you to pick out alkane structure on these types of drawings, because typically alkanes tend to form the framework or the architecture of an overall molecule upon which are present or perched or worked into perhaps more recognizable functional groups. So for instance, in this line structure, if we look at what do we have here, so we're looking at what is A? Well, A is, in this case, a line structure we have, and each of those bends is a carbon, so that's a carbon-carbon double bond. That is, by definition, an alkene, carbon-carbon double bond. So we would recognize that as an alkene. Well, what about B? B here we have a carbonyl carbon flanked on one side by hydrocarbon carbon, written in line form, and on the other side by an oxygen connected to a hydrogen. That is diagnostic structure for a carboxylic acid. And we're just going to run through all of the rest of these. Let's look at what is C right here. C, we have an oxygen atom flanked on both sides by hydrocarbon carbon. That is diagnostic for an ether functional group. You see where I'm going with this now. Let's look at D. Here we have is another carbonyl carbon flanked on both sides by hydrocarbon type carbon. That is diagnostic structure for a ketone functional group. Let's look at structure E here, because this is how these things are written in line structure. It's important to get to know these. What do we have here? Well, it seems like we're starting with a single line, going into a triple line, and then ending with a single line again. What that means is that when we change from single line to triple line, right here, and then back again, right there, That is the presence of a carbon atom. Now in line structure, I remember I had told you that we have carbons at the ends and the bends. Well, the carbon-carbon triple bond, which is, by the way, an alkyne, which we just recognized, is by definition linear. It is, remember, that 180-degree bond angle, so they must be drawn in this fashion. So we would have, indeed, this, this structure E as as an alkyne. We would recognize it as an alkyne. Let's look at the last one, F. Here we have an oxygen, flanked on one side by hydrocarbon-type carbon, and on the other side by a lowly hydrogen. That is, by definition, an alcohol functional group. This, with practice, gets easier, I promise. Right now, essentially, as I said before, I've thrown upon you really the entirety of the rest of the units of the organic chemistry. The next 5 units. Each unit we're gonna go into detail on 1 or 2 or 3 of the different functional groups we are introducing here. But again, this is just an introductory effect. So let's do it again. Let's keep going. Structure A, what do we have here? Oh, bromine, that's one of our halogens. So this must be a halide. What about structure B? Well, let's see. I always start at the carbonyl, C double bond O, flanked on one side by a hydrocarbon-carbon, and on the other side by an oxygen, which is in itself attached to another hydrocarbon-carbon. That is diagnostic structure for an ester. If we look at C, another, we have our carbonyl carbon right here. Notice that we've drawn it here so that the carbon in that C double bond O is at a bend in a line drawing. So we have a carbonyl flanked on one side by hydrocarbon-carbon and on the other side by a nitrogen. That is by definition an amide functional group, which stands in contrast to the next one, D, where we have simply that nitrogen not directly attached to a carbonyl carbon, but rather a hydrocarbon type carbon. That's an amine. Different, slightly different. Amide, amine, one consonant difference. So as I told you before, sometimes we have very, very obvious functional groups. E here, and it's written in line structure. We didn't introduce this one in line structure. It was more in complete bonding structure. But this is a six-membered ring, 6-carbon ring, with alternating single and double bonds. That was diagnostic structure for a phenyl group. Remember that? That was one of our hydrocarbon type organic functional groups. So having been introduced to all of these new functional groups, we are going to circle back and focus the rest of this unit on the study of one particular functional group. And each successive set of units will be looking at different functional groups in more detail within themselves. So we're circling back to look specifically at alkanes. Alkane functionality, with alkanes are hydrocarbons typified by carbon-carbon single bonds, as shown here. Alkanes, by definition, since the carbon is completely single bonded, since carbon is tetravalent, meaning it has 4 bonds emanating from it, the rule of 4, it must have tetrahedral electron geometry around it, around each of these, and thus is 3-dimensional around each of these carbons. Because of this tetrahedral geometry, wherever we measure a bond angle, those bond angles are always 109.5 degrees. They go hand in hand with tetrahedral geometry. One interesting characteristic of alkanes in these carbon-carbon single bonds is that carbon-carbon single bonds allow for free rotation around them. So for instance, if we look at this line drawing right here of 6 carbons, I can tell it's 6 carbons because I count 6 ends and bends. 1, 2, 3, 4, 5, 6. Just saying that because we got to get used to doing that. If I took that central bond, I can actually, since it's a single bond, rotate around it. And it comes up with this structure right here, which if I rotated back around it, perhaps we'd come back to the previous structure. Now this is important because notice that each of these carbon-carbon single bonds in this line drawing has the ability to rotate around it, so that we have the ability to draw this molecule in many different ways so that they may initially look different. They may look like different compounds because they're not expressed the same way. However, we are going to find out that they are indeed all representations of the same compound. This is one of the stark differences between organic chemistry, what we need to know for organic chemistry or understand for organic chemistry, as opposed to general chemistry, where we don't see these. We always have one chemical formula for one type of compound. Now it's a little different because we're looking at these in a more in a sort of sense of shapes and how they're represented. And are these two pairs, are they identical compounds? Are they somehow different? We're going to be answering those questions as we move along. Lastly, alkanes are considered to be what are called saturated hydrocarbons. The term saturated hydrocarbons we're going to be talking about on the next slide. Carbon-carbon single-bonded species, or alkanes, are considered saturated hydrocarbons, whereas carbon-carbon double-bond species and triple-bond species, which are alkenes and alkynes, respectively, are considered unsaturated hydrocarbons. So let's look at what that means. Essentially, we can think of saturated or unsaturated with respect to the number of hydrogen atoms which a certain number of carbons can attain. This determines whether it is considered a saturated or unsaturated compound. To get into this, let's look at a 2-carbon alkane. That's a representation of a 2-carbon alkane. If on each of these carbons, one of their 4 bonds is used up connecting to one another, each of them has 3 more bonds, because of the rule of 4, to attach to hydrogens, which would give that 2-carbon alkane the ability to attain or hold on it 6 hydrogens. We cannot get more hydrogens than that, so it is considered saturated with hydrogens. If I drew on another hydrogen, well, that's a problem now because I have 5 bonds around one of those carbons. You can't do that. That cannot happen. So we have a situation where we can only have 6 carbons, hydrogens around 2 carbons. Now let's compare this with the analog of an alkene, 2-carbon alkene, where 2 of each of the carbons bonds are used up connecting the 2 carbon atoms together. So to satisfy the rule of 4, on each carbon we can only install 2 more carbons apiece for a total of 4 hydrogens on there. That is considered unsaturated with respect to the number that we saw before on our alkane, which was 6. Going down to 4, well, it's unsaturated because 2 carbons can technically attain 6 hydrogens if it's in an alkane, carbon-carbon single-bonded form. So carbon-carbon triple bond is also considered unsaturated because of the 4 bonds around each carbon. In the case of an alkyne, 3 of them are now used up on each carbon connecting the 2 atoms. Thus, each of them only have 1 bond left to connect to their hydrogens, 1 bond apiece, so that's the total of 2 hydrogens, again considered unsaturated, because we know for 2 carbons, the total number of hydrogens that can connect to or bond to 2 carbons is 6, but this is 2, it's less than that, so it's considered an unsaturated hydrocarbon. So let's look at alkanes from an observable standpoint. Physical characteristics of alkane hydrocarbons. There's not much there because they're really actually kind of boring molecules or boring functional groups. The first thing to put down is that typically alkanes as a functional group are considered unreactive. They're not very reactive in a chemical sense compared to the relatively much higher chemical reactivity of other functional groups, such as alkenes or alkynes or aldehydes and that sort of thing. So they're considered unreactive molecules. They're also considered nonpolar molecules. If you remember from general chemistry, a hydrocarbon, which an alkane is, are considered molecules whose only intermolecular force is that of dispersion forces. As a result, alkanes are typically not water soluble because water is not like that. Remember that like dissolves like? Alkanes bearing dispersion forces are not like water, which bears hydrogen bonding as its primary intermolecular force. If we don't have a like dissolves like, it is probable that the alkanes will not dissolve in water, and indeed that is the case. Now, because they are governed by weak dispersion forces, their melting and boiling points increase with increasing molar mass or increasing size. So if I had, for instance, a representative 5-carbon hydrocarbon, a 6-carbon hydrocarbon, and a 4-carbon hydrocarbon, which one would have the highest boiling point? We could predict that because the one with the greatest number of carbons is going to have the highest molar mass. And indeed, we see that one in the middle, 70-degree boiling point. The next one would be a 36-degree boiling point, and then the 4-carbon one would be a 1 degree Celsius boiling point.